Good morning, students. This is M. Prasant Raju, stand before you to continue the classes of Unit 3, Free Electron Theory. In the last class, we have discussed that the merits and demerits of classical free electron theory. Now we are going to enter into the quantum free electron theory. According to quantum free electron theory, we should know the number of field energy states of electrons, the number of available energy states of electrons, and the energy distribution of electrons, how they will be, we are going to learn in quantum free electron theory. If you look at this topic, which is called energy distribution of electrons in metals and Fermi energy, according to quantum free electron theory, there are three most important we should know that. First one is the energy levels are discrete. This is microscopic property. And the second one is the spacing between any two energy levels is very much less, that is around 10 power minus 6 electron volts. And the third property is the distribution of energy levels seems to be continuous. This is considered as macroscopic property. So strictly speaking that, let us discuss about these 3 points here. What is the first point is telling here? The energy levels are discrete. Discrete means which is not continuous. Strictly speaking that, the first property is belonging to microscopic property. According to classical free electron theory, we learned that there will be the energy levels are not filled there, because we are going to learn the three most important, how the energy of electrons are distributed. The second one is their filled energy states of electrons, and the third one is their outermost orbitals of electrons. And we should learn the third one is the distribution of energy levels seems to be continuous. So therefore, strictly speaking, if it is continuous, we are considering it as macroscopic property. If it is discrete, we are considering them as microscopic property. So therefore, let us repeat once again. The first one is the energy levels are discrete. The second one is the spacing between any two energy levels is very much less. So it is very much less in the sense how much it will be. It is around 10 power minus 6 electron volts. The third one is the distribution of energy levels seems to be continuous, and we are considering it as macroscopic property. So next we are going to enter into the proof of this energy distribution of electrons in metals and Fermi energy. What is that? Let us see now. We know that the energy value in three-dimensional is represented as Enx Ny Nz is equal to h square by 8ma square into nx square plus ny square plus nz square. So strictly speaking, let me tell you the formulas that are existing in the letter C is where h is called Planck's constant. It is around 6.623 into 10 power minus 34 joules seconds. And m is called mass of the electron, and whereas a is called the cubic centimeters. It means to say that this nx is called ny, nz, three of them are called the number of energy levels with respect to the three-dimensional axis of x, y and z. Now, this equation, if you see this equation is permissible for the energy levels of electrons in a cubic metal piece. If you are going to consider that the three-dimensional specimen like a cubic metal space, in that we are going to consider that there are three-dimensional axes. My nx is representing along x direction, my ny is representing along y direction, and my nz is representing along z direction. And this equation, the energy levels existing in three-dimensional states is represented by Enx Ny Nz is equal to h square by 8ma square into nx square plus ny square plus nz square. Strictly speaking, that this equation is permissible for energy levels of electrons only in a cubic metal piece. That we have to remember. Then next, suppose if you take the cubic metal piece has a dimension that is around 1 centimeter cube. When we will take 1 centimeter cube, you know, if you are going to find out the volume of a metal cubic piece, as it is three-dimensional, if you consider that its length is 1 centimeter and its breadth is 1 centimeter and its height is 1 centimeter, then if I find the product of volume of the particular cube is L into B into H, then 1 centimeter, 1 centimeter, 1 centimeter square, and 1 centimeter square into 1 centimeter cube. Then we are going to find out the energy state of the ground state energy level, which is given by E111 is equal to 6.625 into 10 power minus 34 whole square by 8 into 9.1 into 10 power minus 31 into 1 into 10 power minus 2 whole square into 1 plus 1 plus 2. If you see this equation, what is the way of substituting the values of Enx Ny Nz and h by 8ma square into nx square plus ny square plus nz square. As I told you in the previous formula that this E111 is representing that My Nx is 1, Ny is 1, Nz is 1. That means the number of electrons with respect to the x, y and z directions is carrying to be taken as E Nx, Ny and z. That means E triple 1 is equal to h square. I has already told you that my h is called Planck's constant. So what is its constant value? Bring it and substitute in this particular place. We will get 6.625 into 10 power minus 34 whole square by 8 into m value. This is called mass of electron. 9.1 into 10 power minus 31 into 1 into 10 power minus 2 whole square. What is this 1 into 10 power minus 2 here? As I told you that the volume of a cubic metal piece is considered as in centimeter cube. If you take 1 centimeter and if you want to convert into it meters, I should write it as 1 into 10 power minus 2 whole square as it is existing in the formula into nx square plus ny square plus nz square. So as I told you that my nx is 1, ny is 1 and nz is 1. If you square it again, we are going to get 1 plus 1 plus 1. So after finishing this, after calculating this with calculator, we will get E nx ny and z is equal to 1.806 into 10 power minus 33 joules. If you are going to convert this energy of the three energy level states into electron volts, we could write it as 11.29 into 10 power minus 15 electron volts. As I told you that 1 electron volt is equal to 1.6 into 10 power minus 19 coulombs, as we are going to consider that this energy state belongs to three-dimensional states can also be expressed in terms of electron volts is 11.29 into 10 power minus 15 electron volts. Now, if you take this is what is known as the maximum spacing between the consecutive energy levels is very less. It is in the order of around how much? 10 power minus 6 electron volts. As I told you in the beginning, the assumptions of quantum free electron theory, in the second assumption, the spacing between any two consecutive energy levels is very much less. That is around the order of 10 power minus 6 electron volts. Now we are going to explain this energy distribution of electrons in metals and how the Fermi energy is linking with this energy distribution of electrons in metals. We are going to explain with graphical representations. If you look at the figure 1 diagram and figure 2 diagram, I should explain like this. Look at carefully. If you see the first figure 1, if you are going to take the dot, if you plot a graph between N of E versus E, let me tell you what is this N of E and what is EF here. This N of E is called number of energy levels, which is taking on y-axis, and EF is taking on Fermi energy level or energy levels is taking on x-axis. If you see this diagram, we are going to get a curve representation like this. In this diagram, in this graphical representation, we are going to consider three important values. What is that? If you see this particular peak, this is called my EF, my Fermi energy at 0 kelvins. Okay, and if you take this white representation curve, in the middle portion of the white representation of the curve, the Fermi energy is going to be observed at room temperature. Similarly, if you continue this dotted lines of white dotted lines of curve reaching towards the x-axis edge, there we are going to take EF plus kBT. Let me explain this continuation. My EF is called Fermi energy adding with the product of Boltzmann's constant with absolute temperature. So strictly speaking, my students, if you see this first figure, it is purely a diagram or a graph in between N of E versus EF. As I told you in the heading of the title of this particular topic, that is energy distribution of electrons in metals and Fermi energy level. My Fermi energy level, strictly speaking, that one important follow-up is going on here. What is that? As long as my number of energy levels is going on increasing, my Fermi energy level is also gradually increasing along with the number of energy levels. And if you see the second diagram, that is figure 2, in this figure 2, if you are going to take both the sides like well, in the left hand side of this well, we have energy, and the right hand side of well, we are going to consider it as EF. My EF is called Fermi energy levels. Strictly speaking, that as long as the energy levels are gradually enhancing, my energy level, my Fermi energy level is also gradually enhancing. Observation points from the graph. If you see the previous diagram, figure 1 and figure 2, there are some observations we should follow here. If you see the observations from graph, the first figure is as the number of energy levels N of E increases periodically with the increase of energy. This is we are observing from figure 1. And if you see the figure 2, the dotted line shows the change in energy of electron at room temperature. And the third point is each energy level can provide only 2 states. What are those 2 states here? As I told you that one is spin up direction. One energy state is in spin up direction and the other energy state is electron is spin down direction. So these are the 3 important points we should observe from figure 1 and figure 2. If you draw a graph between N of E is taking on y-axis and Fermi energy level is taking on x-axis, we should observe that there are 3 most prominent points. First one is number of energy levels increasing periodically along with the Fermi energy level. And the second one is the white dotted lines explains that the change of energy is at room temperature, that is only available at room temperature. And the third one is each energy level can provide only 2 states. One energy state is spin up direction and the other energy state is spin down direction. That means we should understand that the available filled energy states is only 2 electrons that can be filled in a given energy state. If you take one energy state, for every energy state there will be 2 free electrons. If you see that the 2 electrons can be filled in every energy state. Strictly speaking, my dear students, if you see the fourth point, this is similar to or this is resembling that the Pauli's exclusion principle we should remember here. What is Pauli's exclusion principle? No 2 electrons in an atom can have the same number of 4 quantum numbers. So strictly speaking that according to quantum free electron theory and energy distribution of electrons in metals and it is linked up with Fermi energy, our ultimate article is to identify which one is the Fermi energy level here. Suppose if you take the Fermi energy level state is available when the absolute temperature is at 0 Kelvin. Suppose if you see the fifth point, at T is equal to 0, if there are n number of electrons, strictly speaking that my n being even, it should not be odd. So that means the Fermi energy, that is highest energy state level where it acquires, that is available only at T is equal to 0. So that means at T is equal to 0, if there are n number of electrons, strictly speaking that n being even, then we have n by 2 number of filled energy levels. Where we are going to get n by 2 number of filled energy levels? That n by 2th level is considered as highest energy state and we are calling it as Fermi energy level. The next subsequent topic followed by distribution of energy levels is Fermi-Dirac distribution function. Let us see this story of Fermi-Dirac distribution function. Fermi and Dirac are the 2 scientists. They are going to explain the distribution function of energy levels. If you see the definition of Fermi-Dirac distribution function representing that the Fermi energy level represents the probability of finding or probability of an electron occupying a given energy state. If you see that to find out, our ultimate article is to find out this f of E. What is this f of E? Fermi energy level. So, in order to find the probability of an electron occupying a given energy state, the energy states actually occupied by free electrons at any temperature, absolute temperature T, we can apply the Fermi-Dirac statistics. So, according to Fermi-Dirac statistics, the probability of finding or the probability of occupying an electron in every energy state is going to be represented that f of E is equal to 1 whole by 1 plus e power E minus EF whole by kb into T. Let me explain this formula here. So what is this f of E first of all? Fermi energy level. In the previous topic, that is distribution of energy levels or energy distribution of electrons in metals, as I told you that my f of E is called Fermi energy, which is the highest energy level state that is available at T is equal to 0 Kelvin. So therefore, the Fermi-Dirac distribution function is explaining that the probability of electron occupying a given energy state is represented by f of E is equal to 1 whole by 1 plus this is small e is representing exponential term of E minus EF by kb into T. Strictly speaking that this f of E is called Fermi energy level and this E is called energy level and this small e is representing exponential term, kb is called Boltzmann's constant and T is called absolute temperature. So strictly speaking that Fermi-Dirac statistics deals with the particles. The particles is nothing but electrons. If they are having half integral spin, then they were called as fermions. I underline this particular point, which is called what exactly the fermions. Okay, the Fermi-Dirac statistics deals with the particles. They are electrons, sure, but if they have half integral spin, they were converted as fermions. And The so-called Fermi and Dirac explains the distribution functions of the particles provided if they have half integral spin, they will convert it as fermions. So they both told about these fermions. The probability of occupying an electron in every energy state is supposed to be represented as f of e is equal to 1 whole by 1 plus small e to the power of e minus ef whole by kb into t. I can call it as equation. You have to remember this equation here. And in this followed equation, my EF is called Fermi energy level and my kb is called Boltzmann's constant. Let us see the importance of this Fermi energy level and the Fermi-Dirac distribution function. If you see the importance of Fermi-Dirac distribution and the effect of temperature on Fermi function, as I told you that the first equation, that is Fermi energy level f of e is equal to 1 whole by 1 plus small e to the power of EF minus E by EF by kb into t. If you see that from equation 1, the first observation we observing that it is at 0 kelvins. At 0 kelvins, the electrons can be filled only up to a maximum energy level. What is that maximum energy level here? That maximum energy level is nothing but EF0 as representing that EF0. This is nothing but called EF means Fermi energy at 0 Kelvin. So strictly speaking that, my dear students, if you see this EF0, this is one of the symbolic notation of the Fermi energy level at 0 kelvins. That is representing that absolute temperature. If you see 0 Kelvin, this Kelvin is called absolute temperature. So at 0 Kelvin, the electrons can be filled only up to a maximum energy level. That is called Fermi energy. Therefore, my EF0 is called Fermi energy level at 0 kelvins. If you take above F0, all the energy level states are empty states. That is the remembering point here. So that means if you see the following conditions, there are 1 to 2 conditions. Number 1 is called, the first one is called E less than EF. What is the meaning of this? This E is called energy level. This EF is called Fermi energy level. Suppose if energy level of electron is less than Fermi energy level, my equation 1 is followed by f of e is equal to 1 whole by 1 plus e power minus infinity. That means after simplifying this, we will get 1 whole by 1 plus e power minus infinity is 0. Therefore, 1 by 1 that is equal to 1. So, what is the physical significance behind on this first case, that is E less than EF? Let me tell you this. If you see this f of e is equal to 1, that is my Fermi energy level is carrying 1 provided my E less than EF. This is strictly speaking that 100% clearance for the electrons to be filled within Fermi energy level. So that means to fill 100% clearance of electrons that is going to be filled in Fermi energy level, strictly speaking that the first condition should be satisfied. What is that first condition here? My energy level should always be less than Fermi energy level. Then my equation 1, bring all the values and substitute it there as absolute temperature T is equal to 0 kelvins and the Boltzmann's constant is always permanent constant, and after substituting all the required terms in the particular formula of equation 1, we will get f of e is equal to 1 whole by 1 plus e power minus infinity, as my e power minus infinity carrying 0 and simplifying 1 by 1, that is equal to how much? 1. That means when you are going to get the Fermi energy level is equal to unity or 1, it is representing that 100% clearance for the electrons to be filled within Fermi energy levels. We will see the next case, that is around E greater than EF. Suppose if E greater than EF in the second case, what will happen? We will see. If you see the second case, that is when E greater than EF, that is energy level is greater than Fermi energy level, my equation 1 becomes f of e is equal to 1 whole by 1 plus e power infinity. As e power infinity is carrying 0 and it is also equivalent to infinity, therefore the total denominator term is nothing but infinity. Therefore 1 by infinity is equal to how much? 0. So in the previous case we got f of e is equal to 1, that is e less than ef. But in the second case, as e greater than ef, equation 1 is becoming that f of e is equal to 1 by 1 plus e power infinity. That means my Fermi energy level is carrying how much? 0. So what is the physical significance behind on this second case, that is E greater than EF? That means if you are getting 0 here, there are 0% chance for the electrons not to be filled in the Fermi energy levels. That means if f of e is equal to 0, if f of e is equal to 0, there is only 0% chance for the electrons they are not going to be filled in Fermi energy levels. Within the Fermi energy levels, they are not going to be filled because we are getting 0% chances here. If you see the third case, that is the Fermi energy level is equivalent to energy level. So when energy level is equal to Fermi energy level, my equation 1 followed by f of E is equal to 1 whole by 1 plus 1, that is equal to 1 by 2. The total term of the denominator portion is equivalent to 2. If you divide 2 with 1, you got 0.5. What is the physical significance behind on this third case is there are 50% chances for the electrons to be filled and 50% chances are not going to be filled within the Fermi energy levels, strictly speaking. Okay. So did you understood the three cases here? The first case is E less than EF. The second case is E greater than EF. The third case is E is equal to EF. So in the three cases, my dear students, the Fermi energy level and it is the effect of temperature on Fermi function, how it will be varying, you know. The energy level is, when the energy level is less than Fermi energy level, we got 1. That is f of E is equal to 1. There may be only 100% chances. But if you take the second case, E greater than EF, as you are going to receive Fermi energy level is 0, we are going to get only 0% chances for the electron not to be filled in the Fermi energy level states. And when we are going to take the third case, when E is equal to EF, that is energy level is equivalent to Fermi energy level, my equation 1 is followed by f of E is equal to 1 whole by 1 plus 1, you are going to get 0.5. That means 50% chances for filling of electrons within the energy level, Fermi energy level, and similarly the 50% chances that not to be filled within the Fermi energy levels. This we are going to identify. Okay, so that means the effect of temperature on Fermi function, if you see these three cases, that is E less than EF, E greater than EF, E is equal to EF. These three cases followed by at 0 kelvins. That you have to remember. That is why I am putting heading here, the importance of Fermi-Dirac distribution and the effect of temperature on Fermi function. Strictly speaking, that my f of E is called Fermi function. So therefore, at 0 kelvins, how the behavior of electrons, whether they are going to be filled completely, whether they are going to be filled 50% filling or whether they are going to fill 100% filling, that we are going to checking here by taking equation 1, that in 3 of the cases, the first case E less than EF and the second case E greater than EF and the third case E is equal to EF, we are going to get 3 different stages. So in the second case, we are getting 0% chance for the electrons not to be filled within the Fermi energy level. That we have to remember here. And when you are taking third case, when E is equal to EF, equation 1 is giving that Fermi energy level f of E is equal to 0.5. That means there will be 50% chances for 50% chance for the filling of electrons within the energy level. Similarly, as I told you that 50% chances for filling of the electrons, similarly, there may be another 50% is not to be filling the electrons in the Fermi energy levels. This is what is known as the effect of temperature on Fermi function. With this, we have to finish that the portion of free electron theory of metals, as our unit 3 is consisting 2 major portions. The first portion is free electron theory of metals and the second portion is band theory of solids. The second portion of unit 3, that is called band theory of solids, we will see in the next class. Thank you.